Hello, my people. Hope we're doing well. The first video was on simply deriving the sum and difference formulas. What we're going to do in this video is we're going to do some evaluation and change of form and stuff like that. And like I said before, all of this is really kind of like when you did all those things with logarithms and exponents and stuff like that. This is really an opportunity for us to play around with these functions and the identities that show us the necessary relationship between them, such that we have facility in using them for when I actually need to use them strategically in the future. And that's kind of the payoff, okay? So let's go ahead and get started. We have cosine here of 5 pi over 6 minus pi over 2, okay? And here we have cosine of 5 pi over 6 minus cosine of pi over 2. And like I said in the video for our class discussion, the whole purpose of contrasting these two is to remind us that cosine is not, let me repeat, is not a quantity. Cosine is not a quantity, and therefore these are not equivalent. You can't distribute, right, quote unquote, you can't distribute cosine across these values. But we do know the cosine identity, and the cosine identity is cosine u minus v is equal to cosine u cosine v plus sine u sine v. And if that's the case, then it ought to be really simple. Okay, u just happens to be our 5 pi over 6, and v happens to be our pi over 2. So we have cosine of u cosine of v plus sine of u and sine of v. Okay. Now, we simply need to remember our unit circle values in order to do all this, right? Now, cosine of pi over 2 is actually 0. So it actually really doesn't matter what cosine of 5 pi over 6 is. Sine of pi over 2 is 1. Sine of 5 pi over 6, now remember 5 pi over 6 is in the second quadrant over there pretty close to pi, having a reference angle of pi over 6. That winds up being positive 1/2, and this is negative root 3 over 2. This whole term goes to 0, and this sum is 1/2. Well, the reason why that's 1/2 is if you actually take this and this becomes 10 pi over 12. Actually, this can just be unreduced to 3 pi over 6. So 5 pi over 6 minus 3 pi over 6 is going to be cosine of 2 pi over 6, right, which is cosine of pi over 3. Now, is cosine of pi over 3 1/2? It is, okay? But when we look at this, cosine 5 pi over 6, we've already recognized the fact that that's negative root 3 over 2. And cosine of pi over 2 minus 0, this is negative root 3 over 2. Those are not equivalent, okay? On this one down here, I've simply given you a tangent and a sine with different ways of representing values that, unlike the one above, are probably not unit circle values. Now, pi over 3 is 4 pi over 12. Pi over 4 is 3 pi over 12. So really what you're getting here is you're getting tangent of pi over 12. And that pi over 12 is rewritten as the difference of two unit circle values. So in terms of evaluation, we can kind of see the benefit here. But in our difference, we know that that's tangent of pi over 3 minus tangent of pi over 4 over 1 plus tangent pi over 3 tangent pi over 4. Now, tangent of pi over 4 is actually pretty easy, okay? Tangent of pi over 4 is 1, okay? And so what we have here is we have minus 1 and, 1 plus some value times 1. The question is, what is tangent of pi over 3? Well, tangent of pi over 3, and you can think about it in terms of a unit circle, and there are several ways you can do this, but sine of pi over 3 is going to be root 3 over 2, and cosine of pi over 3, we've already established, is 1/2, and therefore what we get is root 3. And therefore, tangent of pi over 12 is root 3 minus 1, and if you want to, turn the denominator around so that it looks all nice and sort of semi-symmetrical, you get root 3 minus 1 over root 3 plus 1. And you can leave it like that. I'm not a big stickler about rationalizing the denominator. That's something that's sort of fallen by the wayside by the time you get to calculus. Now let's go ahead and look at this one. We have sine of pi over 3 plus 3 pi over 4. Now, if you're wondering whether that's a unit circle value, it's not, okay? Because if you just think about it in terms of degrees, 3 pi over 4 is 135. Pi over 3 is 60. So 135, okay, and 60 is 195. And 195 is not a unit circle value, right? It's basically 15 degrees past 180. And so it's pi over 12 basically past 180, so it's 13 pi over 12. But I can get this if I simply remember that my sum formula for, sine of u plus v is sine u cosine v plus sine v cosine u. So we have sine of pi over 3 cosine of 3 pi over 4 plus sine of 3 pi over 4 cosine of pi over 3. Well, like I said before, cosine pi over 3 we've already figured out. That's 1/2. And if that's 1/2, then sine of pi over 3 is root 3 over 2, right? Now, cosine and sine of 3 pi over 4, they obviously are root 2 over 2, but one of them's positive, one of them's negative. Cosine is going to be negative in the second quadrant, whereas sine is going to be positive in that. And we're going to get negative root 6 plus root 2, all of that over 4. Okay? And you can plug it into your calculator and get a decimal approximation if you want. But basically all this allows us to do is that, values that are not unit circle values but can be represented as sums and differences of different unit circle values, all of a sudden we don't have to get an approximate value from our calculator. We can actually get an exact value. All right, let's go ahead and take a look at this one, theta of negative pi over 12. Now I need to find the sine, the cosine, and the tangent. Now we've already done something similar to this because we've noticed that pi over 3 minus pi over 4 is pi over 12. So basically all I have to do is just flip that around and I can get negative pi over 12, right? Because this is going to be 3 pi over 12 minus 4 pi over 12. Okay, and I can also do the same thing with cosine. And then when we get down to tangent, we will deal with tangent in the same way, despite the fact that, once we have sine and cosine, we could just find the ratio between the two. Of course, that'll be a nice way of checking our answer, right? So this difference right here, we have sine of u cosine of v, v, that's supposed to be a 3 down there, sine of v cosine of u. And, you know, I mean, these ought to be really, really familiar values by now. Obviously, the ones that shouldn't take too much thought are the pi over 4. Pi over 3 and pi over 6, especially when you're dealing with reference angles, you're like, okay, which one is, you know, 1/2 and which one's root 3 over 2? Well, for pi over 3, it's the cosine, that's 1/2, and it's the root 3 over 2 for the sine. It's a difference right there, and we're going to get root 2 minus root 6 over 4. Well, it seems like I have seen that value before, and you have, okay? Basically, it winds up being, it's the same as that, right? Well, because remember that pi over 3 and 3 pi over 4 was sine of 13 pi over 12. And so on the unit circle, those would both 13 pi over 12 and negative pi over 12, or if you want to do its coterminal, 23 pi over 12, would be the same vertical displacement into the negative. Just one would be in the third quadrant and one would be in the fourth. Okay, let's deal with the cosine right here. So we have cosine of u, cosine of v. Sorry, that's supposed to be a 3. Why is that a mental block right now? Okay, now remember, when you're dealing with the sine sum and differences, a difference goes to a difference, but with cosine, it's the opposite. And so you wind up with a sum. Okay, now here's the thing. This is the same values as up here, they're just in a different order, right? And so this is still root 2 over 2. This is still root 2 over 2. Sine of pi over 3 is still root 3 over 2. Cosine of pi over 3 is still 1/2. And you're simply going to be adding them. So root 2 plus root 6 over 4. Alrighty, let's deal with the tangent, okay? Now, tangent is going to be tangent u minus tangent v over 1 plus tangent u tangent v. Now, tangent of pi over 4, we know is 1. Tangent of pi over 3, you should know is root 3. 1 plus, and then this is, I keep doing that. Grr. All right, tangent of pi over 4 is 1, and tangent of pi over 3 is 3. And you're thinking to yourself, well, that over that, is that really the same thing? Well, I don't know. Let's see. Okay. And that's a nice way of checking our answer, right? So let's go ahead and check our answer. You know, we know that tangent of pi over 4 minus pi over 3 should be the same as sine of pi over 4 minus pi over 3, or, you know, negative pi over 12. You know, you can put it in the shortened form if you want. I mean, you're simply checking your answer. I'm just trying to emphasize this. So sine is root 2 minus root 6 over 4, and cosine is root 2 plus root 6 over 4, which becomes root 2 minus root 6 over root 2 plus root 6, which, you know, I mean, it doesn't, I mean, you're not factoring in the truest sense of the word because you're pulling out a GCF that's a radical. But there is a rad 2 that is common to both the first and second term, and there's a rad 2 that's common to the first and second term in the denominator, and because it's a common factor in both, you can confirm by means of the quotient identity that you did indeed wind up with the correct answer for tangent, okay? And then, you know, just put the answers, you know, where they're asked for, and done. Okay, now something that I'm sure we are just all really looking forward to let's go ahead and deal with it in terms of inverse trig. Yay! Inverse trig. Okay, now, here's the thing. Remember, sine, or any trig function, is always done of an angle measurement. But you need to remember that arctan of a ratio is an angle measurement. Let's call that alpha. Arccosine of a ratio is also an angle measurement. We'll call that beta. And this is basically sine of alpha minus beta. I mean, you could have called it u minus v to make it line up exactly with what we've done before. But, you know, alpha minus beta, x minus y, u minus v, it's arbitrary. And so if we have sine of alpha and then cosine of beta minus sine of beta cosine of alpha, and if you want to write it out like that first, before you then basically go back to, you know, arctan of 2x, and this winds up being cosine of arc cosine of x minus sine of arc cosine of x and cosine of arc tan of 2x. Okay, well, alpha and beta, we simply need to construct two different triangles to represent them. They don't have to be to scale. They can just, you know, whatever. And it may actually be helpful to call them, you know, to label them alpha and beta so that you know, you don't get mixed up which one you're thinking about and everything like that. So, you know, if you want to say, let's call that alpha and let's call that beta. Now, if alpha, arctan is 2x, then remember it's 2x over 1. Arccosine, cosine ratio is x. The cosine ratio is actually x over 1, so the adjacent over the hypotenuse is x over 1. And this winds up being 1 minus x squared underneath the radical, and this winds up being 1 plus 4x squared underneath the radical. And now we have all three sides, and, you know, that's I mean, this one doesn't even really need to be done, right? So sine of alpha is going to be 2x. It's going to be opposite over hypotenuse. So 2x over rad 1 plus 4x squared times, well, when you take the cosine of the arccosine of x, guess what? It's x. So sine of arccosine of x, so the sine of beta is going to be opposite over hypotenuse, or 1 minus x squared. And then the cosine of arctan of 2x, instead of 2x over, so basically the cosine is going to be the adjacent over that, and it's going to be 1 over 1 plus 4x squared. And so, you know, if you get this in terms of a single expression, because they already have a common denominator, you would basically express it like that. And that is a mess, and I certainly wouldn't expect you to rationalize the denominator. But, and of course this is kind of obnoxious to do this, but what they're trying to emphasize, and of course what I'm trying to emphasize by following their lead and walking through a problem like this, is there's nothing new about this, okay? And doing a problem like this not only is just another perspective on using these identities and gaining greater facility with them, it also helps us to circle back around and remind ourselves about sort of the fundamentals of inverse trig, especially when inverse trig is sitting there as an expression, right? Arctan of 2x, it's notationally long. It's got an A, an R, a C, a T, an A, an N, a 2, and an X, right? It's like eight different things, but it is 8 different strokes of the pen, but it is one quantity. And it stands in there, as notationally large as it is, it stands in there for an angle measurement. And we need to remember that. So, to aid us in remembering that, yep, let's do another one. Alrighty, now this one is going to be cosine. So let's go ahead and label these. I liked labeling them alpha and beta, so let's go ahead and do that again. Okay, and so what we have here is we'll call this cosine of alpha minus beta. And let's do the expansion just with the alpha minus beta so that we don't get bogged down and get distracted by these notationally large inverse trig expressions. And we know that it's going to be cosine of alpha, cosine of beta, plus sine of alpha and sine of beta, which at this point now I can plug them back in and get cosine of arc cosine of x, and then cosine of arc tan of x, plus sine of arc cosine of x, and sine of arc tan of x. Now that I've basically kind of gone to alpha minus beta in order to lay out the identity and then plug back in. Now if you can skip that and you can actually look at arc cosine x and think alpha and look at arc tan x and think beta, then by all means skip over it, you know. But if that's a helpful sort of intermediary step, especially as you're getting used to this stuff more and more, and if that helps you to not get distracted by the notationally large nature of those inverse trig expressions, then do it, okay? Let's call this alpha. Let's call this beta. Now in alpha, the cosine ratio was x over 1, right? In beta, it was the tangent ratio, the opposite over the adjacent. So this is 1 minus x squared. This is 1 plus x squared when you do the Pythagorean. Okay, well, this one ought to be really easy, just like last time. So it's x. Now I need to take the cosine of beta. Cosine of beta is 1 over the square root of 1 plus x squared. Now I need to take the sine of arc cosine. That's going to be square root of 1 minus x squared over 1. And then I need to take the sine of arc tan. I need to take the opposite over the hypotenuse, which is x over the square root of 1 plus x squared. Both of those terms are rational in structure and already have the same denominator. And so it's going to be x plus x root 1 minus x squared all over root 1 plus x squared. And if you're looking for a way to express that as an algebraic expression, which were of course the instructions, then there you go. Okay. I think that brings us to the end of this particular video. In the next one, we'll be doing some verifications and some solving of equations, which, you know, shouldn't surprise anybody. And so that's kind of the way that these have sort of taken shape. It'll probably only be one more video. It may be two more. It just depends upon how quickly I get through the verification and equation problems and how many rabbit trails I'm going to chase down. But if you have any questions on anything in this video, please do shoot me an email or a chat in Teams, and I will get back to you shortly. Bye.